Okay, so today we will begin with new lecture, lecture 31, which is a continuation of last lecture in which we started talking about structure of polymers. So just as a brief recap of these last lecture, so we talked about various types of polymers, and there we look at there are two major categories. One is thermoplastics and second is thermosets. Thermoplastics typically tend to soften with temperature, and they are more softer and ductile. They can be formed easily, and they have a little cross-linking between polymer chains. On the other hand, in thermosets, they are hard and brittle. They do not soften with temperature, and with increasing temperature, they do decompose. So they have different applications depending upon what you require. And then we looked at example of polyethylene and derivatives, where one could see that one could convert polyethylene into various other kinds of useful polymers by replacing hydrogen with other functional groups such as chlorine or fluorine or methyl or cyanide. Okay, and of course, and then we were looking at the polymers from the perspective of their cross-linking. Okay, so generally you have your thermoplastics would be something like that. So there's very little cross-linking between the. So if these are MER units, these are running polymer chains. So they basically make linear thermoplastics. Okay, linear polymer chains, which could be entangled to some extent, but they have very little branching or cross-linking. As the let's say if you increase the branching, so branching may increase like this. So branching could be of same functional group or different functional groups depending upon what things are. So branching doesn't mean cross-linking. Branching just means there are side branches, and these side branches often make it difficult for the polymer chains to move around. As a result, their strength increases. Now there could be cases in which you have cross-linking. So this cross-linking can happen like this. Okay, so these can, if these turn into cross-links like these. Okay, the cross-linking basically means the chains become even more rigid, and this cross-linking is typically done by other functional groups such as sulfur in case of vulcanization of rubber, and this cross-linking leads to substantial increase in the strength of the material, because then polymer chains become even more rigid. And then finally you can have a networked structure, just like you saw in case of silica. You can have quads kind of form in very rarely in polymers, but there is a possibility you can have a network like structure. So these are different types of polymer that we discussed. So essentially here we talked about effect of you can say the increased branching and cross-linking. Okay, so as degree of cross-linking or branching increases, the strength or hardness of polymers typically increases. Now we're going to look at some properties of polymers which make them describe so that we can describe them in different manners. So this is called as the position of side groups. So we can say basically, depending upon the placement of side groups, polymers can be characterized in three categories. One is atactic, second is isotactic, and third is syndiotactic. These definitions are used to describe the position of functional groups on the side of the polymers. So, atactic one would be, for example, you have the case of, in this case, PVC. So, you have these as functional units. So, these are the main atoms. So, this is, let us say, the carbon atom, okay, and then we add hydrogen and some other atom, okay. So, let us say we have one hydrogen here and another hydrogen on the front, and in this case one hydrogen on the front, and we add one PVC group, okay. So, this is basically hydrogen and this is chlorine group, okay, PVC related group. So, vinyl side group you can say, okay. Now, if the placement of these vinyl side is random. So, for example, here you have it here, and then the other thing you have again in this case, let us say the one hydrogens are here and it becomes, let us say in this case here, and let us say in the other case it is now here and hydrogen comes here and the other two hydrogen goes there and there. So, if the placement is random, vinyl group is placed randomly on the MER unit, it does not matter whether in the front or whether in the back, alternating, just randomly. So, this random placement gives rise to, so basically we can say random placement of side groups. This makes what we call as a atactic structure, okay. If you have isotactic, in that cases you have these as the carbon atoms, okay, and on the back of every carbon atom you had as if you had one like this. On the back you had one chlorine, on the front you had hydrogen, and in this case one hydrogen will come like that, another hydrogen will come like this, okay. All right. So, if so on the so this arrangement is basically side group being on the same side. So, this means it is a isotactic arrangement of molecules or side groups, and in some cases you can have alternating arrangement. So, instead of having in this fashion, you may have so for instance in this case the first one may go there with hydrogen atom being here, the second one may have hydrogen atom sitting on the back, and this atom will coming on the, so this is hydrogen atom and this atom will come on the front. Okay. So, this is back, this is front. Similarly, in the next one it will get onto the back and here it will come into the, this will come into the front. And if I make another one here just for the sake of clarity, so this hydrogen atom will go on the back and this will come onto the front, and the other two will go in the similar fashion. One hydrogen atom, second hydrogen atom, one hydrogen atom, second hydrogen atom. Okay. So, this alternating you can say regularly alternating arrangement of side groups. This makes what we call as a syntactic structure. So, this is isotactic, sorry, what am I writing, just one second, this is atactic, this is isotactic and this is syntactic. Okay. These are three, so you can have PVC, you can have, if you have benzene ring on the side, if you have methyl group, it can happen in any of the cases. So, you can also make things like copolymers. Now, copolymers, you attach two polymers. So, for example, we have cases of the PVDF TRFE, right? PVDF is polyvinyl difluoroethylene and TRFE is trifluoroethylene. Now, this basically these two copolymers can arrange themselves in a fashion so that they are present in such a manner so that there are repeating units of, so for example, you can have unit of PVDF, then you can have unit of TRFE, and there may not be any, so it can do itself in this fashion. This is a very straight chain, normally you will not have such straight chains. So, this sort of behavior where you have this PVDF, you can have TRFE and so on and so forth. So, this will make a copolymeric structure of two materials. So, copolymers, they can be, copolymers also can be arranged in such a fashion so that you have regular placement of copolymers or you can have random placement of molecules. So, it could be both regular arrangement, which is very unlikely, and you can have random, and this is what is more common, and this leads to loss of crystallinity in polymers because so this is one way of doing it. Another way of doing it could be you have one polymer chain like this, okay, this is one polymer chain and the other polymer can attach itself as branches. This is also one possibility. Okay. So, they can attach along the length in this fashion. So, you can have along the length. So, they can have repeating units which may not be exactly repeating because they are randomly placed in many cases, or you can have the sideways arrangement of polymers. So, these are basically, you can say, copolymers. All right. Now, typically, as you have seen, molecular weight effect we described last time. So, small molecular weight will mean smaller chains, and higher molecular weight will mean basically larger chains, longer chains. And it turns out that as you increase the molecular weight, it becomes more and more difficult for the chains to basically to arrange themselves. So they entangle, they are entangled more when the chains are longer. So basically you can say the entanglement increases as chains become longer. And what is this to do with? Molecular weight. This is to do with the increase in the molecular weight. So basically, and this leads to increased, for example, tensile strength. So higher molecular weight, for example, higher molecular weight polyethylene will be more stronger as compared to lower molecular weight polyethylene. You have two forms available in the market, HDPE and LDPE, low density polyethylene and high density polyethylene. So basically both tensile strength as well as in some cases modulus as well, they tend to increase with increasing entanglement, which could be as a result of chains becoming longer, which could be as a result of increasing molecular weight or degree of polymerization. So now let's look at other kind of polymers. Some of them, this category is called as elastomers. Okay. All right. Elastomer, the properties of elastomers are they demonstrate rubber-like elastic behavior. So rubber-like elasticity they have, and basically they have long chain molecules with some degree of cross-linking. Okay, and so you can have this kind of structure, and these are cross-linked. Okay, so these are cross-links, and so these segments between the cross-links are the segments which are basically mobile segments, mobile portions. They can move around, they can flex themselves, and these cross-links points are the anchor points. So they move around these anchoring points. So these are the points at which it is cross-links. So they get anchored, but between them, so this distance between the two anchoring points is fairly large. It could be of the order of few hundreds of monomers. So it provides sufficient spacing between the two anchoring points for the chains to be flexible. And these elastomers have this natural tendency for bending and recoiling. So they have excellent bending and recoiling properties. The segments that you see here, these segments here, they can flex and move at room temperature. So these are mobile portions at room temperature. So they provide enough flexibility to the elastomers. So for example, let's see the case of what we call as nylon. Okay. In nylon, what happens is that you have, let me make nylon structured. So you have CH2 group, goes like this, CH2 group, and then you have carbon, and then you have nitrogen, then again you have CH2, you have CH2, you have CH2, again a CH2, again a CH2, and again a CH2. So you have 3 of these CH2s, and then they get connected to N, and then they have C. Okay. On the bottom side, another chain, you will have CH2 and then again C, and this will be linked to N, and here you have CH2, 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 and then I think you will have here, instead of N you will have, so this will be CH2, and so hang on just one second. So we have CH2, CN, CH2, 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 and then we will have N, and then we will have C. So then we will have CH2 again. So we got missed out somewhere, and the C and N here, they will get connected to NH and O. So this O will make double bond with carbon, this carbon will make double bond with O, and they will be hydrogen bonded with the NH group on this side. So these are, you can say, so basically you have this polyamide group here, which is CONH. These, so you can you have one here, one there. The CONH groups are connected to each other through hydrogen bonds, and these hydrogen bonds which are present between the chains, they are more stronger as compared to secondary van der Waals bond. And in this case, the monomer, you can see, monomer will become NH, CH2, 6 repeating units, 1, 2, 3, 4, 5, 6, and then NH again, then CO, CH2, 4 CO. So this will be the repeating units in this structure. So this is a pretty long, pretty tough, big monomer, and so this whole functional, so these chains which are made up of these monomers, they are connected to each other through hydrogen bonds, and these segments are fairly large. As a result, they allow flexibility of this nylon. So nylon is a very well known flexible material. So another example that you have, you know about it, is wood, right? Wood is also fairly flexible. A lot of trees can bend easily, right? They don't break. When the wind blows, they can flex in either direction, and this is possible through arrangement of so basically cellulose chains can withstand substantial forces. So what you have here is basically these cellulose groups, and I'm just going to draw the monomer. So you have OCH, which is connected to CH, O. So then connected to CH. So these are the monomers. So N. So this will make a basically cellulose structure, and this will provide very excellent strength along chain axis. which is basically a longitudinal direction. So chains are aligned in this fashion in the wood structure. These are cellulose chains. There is very little of cross linking between them. They are basically, it's a fibrous structure. Okay, fibrous structure where chains are aligned without much entanglement in the longitudinal direction. So this is the tree longitudinal axis, and they have excellent strength along this axis. And then we have this thing called as natural rubber. And this natural rubber is basically it's an isoprene molecule. Okay, so it's called as isoprene molecule. Okay, and here what you have here is CH double bond C H C CH3 double bond C H H, and this basically converts into so you have H H H CH3 H H. So you can see you earlier had two double bonds which get broken. You have only one double bond. As a result, you have this monomer, and this can be attached. Now these are, so you can see there is a bit of spacing there. So this is spacious, this side is spacious, this side is not spacious. So the spacing allows the rubber molecules to flex. So this can go in this fashion, it can bend because there is a spacing on the. So this is basically rubber molecules flexibility is reason because there is a lot of spacing on one side. There are more functional groups on one side than on the other side. As a result, it can flex. Now there is a treatment which is done to rubber which is called as vulcanization. Which is basically treatment with sulfur. To make it stronger, and because sulfur makes covalent bonds with carbon. So when you do the treatment with sulfur, then what happens is basically you have these CHH, CH, CH3, CHH, and you add sulfur here. So between these you will have sulfur, and there will be another molecule here. And the sulfur basically gets attached here. So otherwise you will have weak van der Waals bond, but the sulfur will ensure to attach. So how will it attach? It will, so this sulfur basically attaches itself in this fashion. So it breaks the double bond again. So this double bond goes off. What you will have here is basically sulfur attaching itself. So this hydrogen can go here. This is how it attaches itself. So it provides cross links. So these are cross links now. The empty spaces are now filled with sulfur, right? So these are cross links. If I draw them using different color, these are cross links. So it becomes, this now becomes a solid mass, and cross linking can convert a natural rubber into, so cross linking, let me just write it again. So cross linking can convert natural rubber into a elastomer. So this is with little degree of cross linking, and then it can convert this to something called as ebonite, which is heavily cross linked. So this is no cross linking, this is light cross linking, and this is substantial cross linking. And as a result, the natural rubber has a liquid like behavior. It is liquid like, this is elastic, soft, basically soft rubber, and this is hard and brittle. So the same material can be converted from liquid like material to a solid which is soft to hard and brittle. You already are aware of bakelite. Bakelite is very hard, and that is how bakelite is made. So this is how the cross linking changes the material's properties in polymer. So for example, tires, the tires that we see applications are in tires, right? Tires need to be hard, so they can't use natural rubber. They have to be some degree of cross linking to make them tough. Of course, tires are composites, there is something else in tires, but the rubber that is used is cross linked. So if you so this is how you basically this is how, if you increase the degree of cross linking, you can make a rubber stronger, harder, and more useful for many applications. So let me summarize basically here that polymers are essentially non-crystalline or you can say semi-crystalline solids so polymers and glasses, okay. They are non-crystalline or semi-crystalline solids. Polymers can be linear chain polymers, or they can be heavily cross-linked polymers, or they can be copolymers. Depending upon the degree of cross-linking, the strength, tensile strength, modulus, hardness of polymers can be increased substantially. And by changing the functional groups on polymeric chains, you can again modify their properties, make them stronger, change their melting point, change their glass transition temperature, and then by controlling the degree of polymerization, which is the number of molecular weight of the polymer, you can again achieve the same characteristics. So they are fantastic materials. The key parameters in them are side groups, degree of polymerization, cross linking, right? These three can affect the properties and their behavior, okay. So we will stop here. We have finished the polymers and glasses now. We will now move on to structural characterization using X-ray diffraction, okay.